just making sure the slideshow comes up properly here. That looks good. So are you, Adil, are you seeing the first slide here?
Yeah, it's a bit small. I can see some of your menus there, like
Okay.
show taskbar and so on. Are you on full screen yet?
I think I am. I don't know. There's an easy way to fix that.
Well, what's it, David? What is it meant to say on the slide that you're presenting at the moment?
Frustrated crystals on curved surfaces.
Okay, that's fine. Okay.
All right.
I think what's shown is just the presenter side of the presentation and not the actual side that would show.
Okay, so
maybe you can click on display settings.
Very good, thank you. Let me see if I can do it. Thank you. Okay, and then
and swap.
Okay, good. Ah.
Oh, thank you very much, Michael. That's fantastic.
Thank you so much. Okay, and I might hold up a few instructional props along the way, and so if there's a setting on your screens where you can actually see this and see me, that might be useful at some point, but not essential at all. Okay, so I'd like to thank Adil for organizing this thing, and thank you all for coming. I think I saw Greg Grayson there, and we're going to have the benefit of a talk from him at our place tomorrow, so I'm looking forward to that, Greg. And this is just an introduction, perhaps not so necessary for this particular group, but many of us in this audience, including my friend Jean-Francois Sadoc, have an interest in frustrated crystals on curved surfaces. And over the years, there's been some beautiful experiments which have motivated a number of us. And what I'm showing here is this idea of grain boundary scars, which you can see on various spherical surfaces where colloidal particles on an oil droplet in water will try to crystallize. And there are, of course, 12 extra disclinations on a sphere just because of Euler's theorem, but then you can make other things like these catenoids and so forth. Here's another picture where the 5-7 construction reveals one of these grain boundary scars. And one of the things that was done way back in 2003 by Andreas Bausch et al. Was to look at different ratio of droplet radius to particle spacing, and for these ratios, count how long the scars were, how many excess dislocations appeared to screen out these disclinations. And let me see if I can find a way to use a laser pointer here. So are you seeing a laser pointer moving around, Adil, for example?
Yes, I am. Sorry, I was trying to unmute myself. Sorry, David, I think I've muted you by accident. I'm really sorry about that. Yeah. David, I think I've unmuted you by accident.
Okay, are you hearing me now?
Yes, sorry, I was trying to unmute myself and then I unmuted you by accident. Many apologies.
Many people have wished that I would mute myself on various occasions, but perhaps not this one. All right, so anyway, one of the in this ancient review here of old work, one of the things we were able to calculate was this slope of the number of excess dislocations per disclination, and there's an exact result for that. That seemed to agree with the experiment and so forth. And one of the ways that we found useful, meaning Mark Bowick, Alex Trapace, and myself, was to look for ground states on the surface of a sphere in terms of these defects, rather than focusing on the particles themselves. This is an interaction between these disclination defects. Many of you know that there's a 5-7 disclination pair that represents a dislocation in this way of thinking about things. And solutions of the biharmonic equation of elasticity on a sphere leads you to this set of interacting charges. That does seem to describe fairly well what happens on spherical colloidal assemblies as the geometrical frustration forces adjacent crystal rows along lines of longitude together. But liquid crystals are easier, and you can, I think, make a lot more analytic progress with them. They, of course, also have frustration. And here's a very nice experiment done in Dave Waits's lab, again, some time ago by Alberto Fernandez Neves, where you're seeing with cross polarizers a defect arrangement of a liquid crystal shell, a nematic liquid crystal shell, where the nematogens are on average in the tangent plane of the shell. And I don't know if any of you can see this baseball that I'm attempting to hold up in front of the camera, but it has amazingly 4 defects sitting at the vertices of a tetrahedron. Why the American baseball has this tetrahedral symmetry that reflects nematic liquid crystals, I don't know. The patent for this baseball structure is like in 1865 or something. So maybe they knew something that we didn't know until the 20th century. In any event, that's one experiment. There's another version. This is a softball, but it also has this, you can draw this nice nematic texture on it. Here's a polar arrangement where a polar vector field on a sphere has 2 defects instead of 4. Here's a recently explored example of tetradic liquid crystal order, which seems to arise in the cells of a shrimp, in the epithelial cells of a shrimp, which can also in principle be curved. This is an illustration of an active matter experiment done in the laboratory, again, of Andreas Braus, also Zvonimir Dojic was involved. And what they did was to have active matter where the system consumes energy, and with microtubules and molecular motors interacting with these vesicles, you can get dynamic motion where these defects, in this case 4 defects, orbit around the surface of a sphere. And some of you may know about this hexatic phase. So that's an example of a 6-fold, not a 4-fold or 2-fold symmetric liquid crystal. And there's some evidence for hexatic order with these liquid crystal-like behavior in cell colonies that undergo the epithelial to mesenchymal transition. And this purple hexatic phase is a relatively small part of the phase diagram, but it possibly is important because there's a diverging shear viscosity. You can show pretty convincingly that you have a continuous hexatic to solid transition. The shear viscosity diverges almost like a Vogel-Fulcher law with a very strong power, exponentiated power law. So anyway, there are lots of these liquid crystal examples, and they're easier to think about, I think, theoretically. And I want to tell you something about the ground states and the rest of this 40-minute lecture of p-fold symmetric liquid crystals. We call them p-atic liquid crystals on cones. And for a long time, I thought cones were likely to be boring because, as you guys know, locally, the Gaussian curvature is 0. But I hope to convince you, probably many of you already knew this, that it's a much richer problem than that. And we'll see even in flat disks, there's also an important role here of boundary conditions. So I'll talk about some parallel transport on a cone and try to convince you that this is really the soft matter analog with a cone of the Bohm-Aronoff effect. So again, probably in your elementary physics courses, you might remember if electrons go on opposite sides of a solenoid, where the field is concentrated in a very thin cylinder, that's like the apex of a cone from the point of view of geometrical frustration. There's a vector potential outside the solenoid, even though there's no field, and that vector potential interacts with the electrons and causes these famous interference fringes. Something a little different happens on cones, but the mathematics is very similar, and there's a very simple vector potential description. And we'll see in this discussion, this talk on the ground states of say pneumatic liquid crystals or p-atic liquid crystals on cones, the boundary conditions matter. There's this lovely sort of Christmas tree chiral texture here with free boundary conditions for pneumatics on a cone. But if you have a tangential boundary conditions at the base of the cone, you get defects that are trapped inside the cone, and some of them like to annihilate themselves on the apex, and some of them like to stay on the flanks. And so we've been trying to construct a theory of that. And we is Grace Zhang and Farzan Fafa, who are, I think, both in the audience. If I get any hard questions during the question period, I'll probably turn to them. But that's an outline of where we're going. Okay, so I like liquid crystal order on cones. That's probably already evident. And although they're locally flat, I think of them as a kind of fundamental or problem of geometrical frustration. If you can't do a cone, then the other problems are probably even harder. And one of the things that we know about geometrical frustration that makes cones interesting is, as you'll see, that if there are defect charges like disclinations on these cones, they not only interact among themselves, they interact with a kind of delta function of Gaussian curvature, which exists on the apex of the cone. There's some nice work on cones, by the way, by Dan Beller and Randall Kamian and Massa with smectic order. I won't be talking so much about that, but I'll be talking about liquid crystal order. And there's a geometrical potential that I first learned about from Vincenzo Batelli and Ari Turner. And this geometrical potential that interacts with defects over long distances on the flanks of the cone and other problems with non-zero Gaussian curvature has the Gaussian curvature as a source term in a Laplace equation. And so for a cone, as I hope to convince you or remind you, that Gaussian curvature is a delta function at the apex. And so this is the basic Poisson equation for this geometrical potential. So that's one motivation. The other is that they occur a lot in biology. And so in particular, here's some cones formed by the polyps in a coral reef. I don't know whether this is crystalline or liquid crystal order here, but it's certainly cones, and there's certainly delta functions or approximate delta functions of Gaussian curvature at the apexes of these cones. And of course, pine cones are called pine cones for a reason. They too are cones. This is probably more of a crystalline order on cones. And as some of the audience knows, cylinders are actually kind of interesting if you look at packings on cylinders. But I think cones are perhaps even richer, as I hope to show you. Okay, so first thing I want to mention is that we're talking about some beautiful work that Grace Zhang has done studying ground states of various types of liquid crystal order in a conical context. But even in flat space, even if I have a disk, it's important to realize and emphasize the effect of boundary conditions. So this is a kind of what in liquid crystal literature would be called a Myers-Salpa lattice model. It generalizes a pneumatic problem that they looked at to a p-fold symmetric liquid crystals. And there's this continuum energy. It's the energy of an XY model. It's the energy that would go into a Kosterlitz-Thouless theory of vortex unbinding transitions or defect unbinding transitions. But if we're at zero temperature, and I'll mostly talk about zero temperature today, a disk, a circular disk with free boundary conditions is absolutely boring. There's no frustration. The system will all be pointing in a particular single direction in this polar example. But as Grace showed, and maybe some of you already know, if you have tangential boundary conditions, as shown down here, defects are forced in just by the boundary condition. So if I have a disk of radius r, there's no Gaussian curvature yet. There'll be a single defect at the center, the single vortex. But as soon as you increase p to other values like 2, 4, and 6, the defects fractionate. They repel each other. This is the condition for a p-fold symmetric order parameter to come back to itself mod 2 pi on any closed circuit that would define what's going on with these defects. And you'll get, in general, p of them inside a disk if you have tangential boundary conditions. And they head out towards the edge, but there are image charges that, image defect charges that prevent them from going all the way to the edge. And one of the nice results that we learned about from Farzan Fafa is the function of p given a disk of radius r. This formula seems to describe the numerical results pretty well. But I now want to ask, what happens when we take these flat disks and make them into cones of various kinds? And so here's a primer on the differential geometry of a cone. This is one set of coordinates that Grace and I found useful, and you may be quite familiar with it. There's a metric. The metric is flat everywhere away from the cone. Involves the sine of this angle alpha that the cone makes, the half angle of the cone. And as you'll see, we can tune the geometrical frustration by changing this angle, this angle alpha in various ways. And if you want to reveal the magnitude, the strength of the Gaussian curvature, which is surely present at the apex of this cone, one easy way to do it is to use the Gauss-Bonnet theorem, which again, a number of you know quite well. It says that the sum of the integrated Gaussian curvature, say everywhere above this circle on the cone, or everywhere above this circle, for example, plus the integrated geodesic curvature around this edge, which is something you can calculate for a cone, is equal to 2 pi times this Euler characteristic. And the Euler characteristic for something with the topology of a disk or the topology of a cone is 1. And as a result, you find that this integrated Gaussian curvature is 2 pi times 1 minus gamma, where gamma is the sine of the cone angle. And that's independent of how far down you are. If you just calculate this thing, you'll find that it's independent. And it basically means there's a delta function up here, regardless of whether you're at R0 or capital R, etc. There's a delta function strength of Gaussian curvature. So in that sense, this is a kind of fundamental problem for frustration. It's almost the simplest thing you can have with a non-zero Gaussian curvature. And some of you may have done this with your students, but if you can see me, I have a thumb, and you can do this at home or in your office, pointing upwards at my nose. If I slide my thumb up to the top of my head, I come down to my ear and go around like this, the thumb has rotated, as is well known, by 90 degrees, by pi over 2. And that turns out to happen on a cone. And in fact, Grace Zhang worked out the parallel transport coefficients from this metric and with the Christoffel symbols and stuff like that. And if you go around on a loop that encloses the apex, any vector will rotate. For this particular cone angle, it happens to rotate by 180 degrees. It rotates by a different amount. This is a top view. This is kind of the Bohm-Aronoff view, where this tip would be like the solenoid, and then you go around opposite sides of the solenoid, different things happen. I'm going to show you some of Grace's beautiful numerical minimizations for various p-atic crystals on cones in a minute. but I want to tell you a nice computational trick, which we found useful. If you just try to take a cone of arbitrary angle and put a mesh on it, say a triangular lattice or a square lattice, in general, you won't be able to do it, just like we can't make a regular lattice on a sphere. That cone angle gets in the way, except at special cone angles of commensurate curvature. And so, again, this is certainly fairly well known. There's a set of special cone angles that allow you to drape a regular triangular or square lattice over the entire conical surface. And for triangular lattice, these special cone angles are 1, 5, 6, 4, 6, 3, 6, 2, 6, and 1/2. For a square lattice, it's 3/4, 1/2, and 1/4. So we can add, two more not different, distinct cone angles. These control the strength of that delta function of Gaussian curvature. And so here are these meshes for the triangular lattice case, and we'll be solving Meyer-Sopa type energies, defining ground states for these very special cone angles to just make the computational make the computation simple. We don't want artificial grain boundaries in our mesh. So that's what I'll be focusing on.
May I interrupt with a question / comment? Yeah, sure. That's
course.
Rob here. Hey, so
Hi.
David, hi. Are you actually going to restrict to the case where your delta charge is positive? Because I mean, obviously there are lots of negatively curved cone points.
Absolutely. And what I'll talk, thanks for the question. And I don't mind interruptions at all. So if a deal will permit, don't hesitate. So there are, we call them hyperbolic cones. And you could put, basically look at liquid crystal order on a triangular lattice that you would make out of a 7-fold disclination. We don't have a lot of results on that, but some of them we think we can take over from positive delta function of Gaussian curvature to negative delta function. So I think that's a very nice comment, and I agree. Hyperbolic cones are certainly quite interesting. Any other questions at this point? Okay, we're going to be minimizing the cone energy with a kind of tunable geometrical frustration, which is going to show up in terms of a kind of Christoffel symbol. This is the lattice analog of the kind of vector potential that comes into this conical Bohm-Aronoff effect. And so here's this vector potential. It has essentially the analog of a zero curl on the flanks of the cone everywhere except at the apex, but it affects things arbitrarily far down the flanks, just like the Bohm-Aronoff effect can produce interference of electrons going on opposite sides. And the radial component is 0, and here's the component of this vector potential in the theta direction. It's proportional to this frustration parameter gamma. And here we have the different kinds of rotations. It's a tunable frustration that shows what happens when you take just a p=1 order parameter, but you can do the same thing for a 6-fold or 4-fold symmetric order parameter and see how it rotates. It rotates by a different amount, independent of how far you are down the flanks, only depends on the cone angle. Now, of course, an actual order parameter won't do this. It won't have an abrupt 180-degree discontinuity, for example. That would produce an infinite energy or a very large energy on a lattice. And so it'll try to spread itself out. And some of you may already realize that what we have here is a set of kind of stacked Möbius strip problems. If I allowed these vectors to relax and drew them on a Möbius strip, they would get rid of the discontinuity. They would smooth it out. There'd still be an energy cost. And there's at every distance down the flank of the cone, there's a different kind of Möbius strip, and we stack them up to get the total energy, at least in a simple context that works well for free boundary conditions at the base. So that's where we're headed. And of course, there can be defects. There's effectively a defect at the apex of the cone. We sometimes call it the central charge. And this central charge will interact with other defects. I'll talk about that in a minute. But even if we don't worry about the apex, we want to be able to make loops and do these loop integrals to define our defect charges. It's very straightforward on the flanks of a cone. If the loop doesn't enclose the apex, it's a little subtle when it does enclose the apex, but we can handle that as well. And one way to do this is to take these loops and to take these cones and just cut them open and flatten them into plane. Not the most elegant way perhaps to do it, but it was the way that at least helped illuminate the physics with the free boundary conditions. So again, there's this frustration parameter gamma. Alpha is this cone angle, or cone half angle. And you can show that if you take the cone, squash it out in the plane, of course, this loop here might become something like this flank loop here. And then this thing that goes around the apex now comes around here where there's boundary conditions required to match the order parameter on what happens here versus what happens here. And there's a host of different angles, a whole zoo of angles, but we'll end up, for now anyway, thinking of this as an XY model in flat space characterized by this polar angle phi, and of course this radial coordinate r, but phi doesn't go from 0 to 2 pi, it goes from 0 to 2 pi times gamma, where this is the cone angle. So if alpha is a half, then I'll have something which is an entire disk flattened out completely, but we'll be interested mostly in what happens when gamma is less than 1. And it turns out to be possible to take this problem back here with a vector potential and to flatten it out so it just looks like your friendly flat space XY model in terms of this angle psi, which is an angle fixed in a fixed coordinate system in the XY plane. So this is the usual angle that many of us use to explore, for example, Kostelos-Dawes transitions. But the integral over phi, as I said, goes from 0 to 2 pi gamma, and you need boundary conditions when you do this flattening procedure. I'm not going to go through the detailed arguments, but if phi goes from its initial value to 2 pi gamma, for example, if it goes from 0 all the way here, there's a boundary condition that requires this to join smoothly, and it picks up two contributions to what relative to what it had over here as I go around. One is from the apex, so you can think of this as a kind of geometrical charge from the apex, and then from whatever number of defects are inside this red loop will contribute. They have a charge 1 over p for p-atic liquid crystals, and if there are n of them, you'll get this extra piece. And that turns out to be enough to figure out everything with free boundary conditions. Contribution from the apex, defect charges absorbed at the apex, and you can show that this n has to be an integer, and what you can do is combine things together to get an effective apex charge here, and then you put in various values of n here and find out which one produces the least geometrical frustration. You can compensate for what the apex is doing by having the apex eat some of the defects and absorb them. And so some values of gamma and p, you can find an n that'll make this 0. In that case, the energy is 0, but most of the time you can't, but you can minimize the effective defect charge at the apex, and the energy is logarithmic in the size, as you might have guessed, and it goes like this effective charge squared, and we can calculate this coefficient. So to make the story of the free boundary conditions at the base complete, let me just say that when Grace does these minimizations and combines it with this theory there are no defects on the flanks. They all commit suicide by going into the apex, if there are any, and there's none left on the flanks. So these are smooth textures, but there's something at the apex in every case. And there's this table as a function of all these cone angles that are easy to simulate and various values of P. And these are her apex charges. And first sight, when we first got this, there's this bewildering array of charges, but they all come from this simple minimization. And if there is a net defect charge, you can collapse them all onto a single universal curve with the only adjustable parameter being a core energy of the composite defect at the apex. So that seems to be what happens for these free boundary conditions. But I wanted, I'll say one more thing about free boundary conditions, then I'll spend the rest of the talk on what is perhaps a more interesting problem, which is what happens when you have tangential boundary conditions. So,
David, can I ask a question on that core energy?
Please. Yeah.
Is that independent of this fractional charge?
As far as we can tell, I think it probably does depend on the fraction. That's a great question. Probably does depend on the size of the fractional charge, but it's a weak dependence, and it'll depend on microscopic details like whether it's a square or triangular lattice. But it won't. The large RB part will be independent of that core energy. But thank you for the question.
Okay, thanks.
Yeah, other questions? Okay, so what's going to happen at finite temperature? The short answer is we don't know. I don't know at least, but I'm hoping to persuade one of my colleagues, Paul Hanakata, to do computer simulations of these Myers-Sopa models on a cone with perhaps these regular lattices. But I think I know what might happen. So here is a classic picture of Debye-Huckel screening, but I want you to think about this in the conical context, and so it's kind of a quasi 2D Debye-Huckel screening. So there's going to be this charge, this effective charge at the vertex of the cone, and no defects at 0 temperature, but of course if I go to finite temperature I get defect pairs. And I think there's a kind of Kosterlitz-Thouless transition on a cone that could be studied here. I like cones because you can take the thermodynamic limit easily. It's much harder to think about, spheres because there's these disclinations everywhere. Here, there's disclinations everywhere in the ground state on a sphere. But here we can just, for the free boundary conditions at 0 temperature, have a charge down here and ask, how does that charge screen as I increase temperature? And so what I show here are the blue and the red dots are supposed to be, give you the impression of plus or minus 1/p defects. And these will be tightly bound a la Kosterlitz-Thouless theory at low temperatures. And there'll be an effective potential by which they interact with this central thing, which is just a logarithm. That's what would happen at 0 temperature if you force them in to the ground state. But there should be a phase transition, unlike a 3-dimensional Debye-Huckel screening where you always have unbound charges. Here, and unlike 1 dimension where they're always bound, 2 dimensions is a borderline case. And I don't know that anybody's ever studied it carefully, but I think these cones may be a way to do it in 2 dimensions. And in 2 dimensions, there's a phase transition where the thermally excited, I think, bound plus or minus 1/p defect pairs, that they renormalize the central apex charge, but then they eventually produce screening at large distances, and there's a Debye screening length, and it has this characteristic divergence, this very strong divergence. So we hope to study that in the future. The simplest case would be these free boundary conditions. So in the remaining time, not much, maybe 5 minutes or so, maybe a little bit more if a deal is generous, I want to tell you about tangential boundary conditions on a cone. So we already saw they're different for a disk. They're incompatible with parallel transport. Okay, here's tangential boundary distance. I start here, I go around with tangentially. If I do something here, it happens to be counterclockwise. It wants to rotate out of the plane of the base. So something new has to happen here. I have a picture here of a sine alpha equals 1/2 cone. And if you can see my camera, here's an actual little model that I made from one of Grace's simulations. And if you look on the flank of the cone in this picture right here, and the cone I'm holding up, and my finger is in front of it now, there's a +1/2 defect, a standard pneumatic defect on the flank, but only one. And if this were a sphere, like in this baseball picture here, you can see that topologically, a cone is equivalent to the northern hemisphere of something. It just has all the Gaussian, the northern hemisphere of a sphere, it just has all the Gaussian curvature concentrated at the North Pole. But here on a sphere, there are two, and there's a total of 4, of course, in general. But what has happened is that one and only one of the 2 defects that should be there by topology on the flanks has been eaten by the apex. And so that's, I think, a kind of interesting phenomena. One of the expected, the 2 expected +1/2 defects has been eaten. And here's eating more systematically for hexatic order on a cone. This is what we've already seen for a disk. And these are these cones with a 6-fold hexatic order parameter in a Mayer-Salpa model. And you can see that the defects, you start off with 6 defects, and then you go to 5, 4, 3, 2, 1, and they successively, the cone, these defects are attracted to the positive Gaussian curvature of the cone, and they get eaten, but not all of them. And so these 6 fractional defects are eaten up. And this was, we thought, quite intriguing and puzzling until we started to interact with Farzan Fafa, who is in the audience, and who is a scientist who knows his way around the complex plane. And he attacked this problem using isothermal coordinates, which is an elegant way to do differential geometry in 2 dimensions, where the metric ends up all being collapsed into this single function phi of z and z bar. Z bar is a complex conjugate. And this function depends on this central charge at the top of a cone. I will leave it to him in private conversation to explain the details. We're now writing this up, but this gives rise to that geometrical potential that was found already more generally by Vitelli and Ari Turner. And it allows the defects not only to interact with themselves on the flank of a cone, but to interact with the central charge. So there are logarithmic repulsions, of course, between the defects and the cone flanks. And what Farzan finds is that there are 3 different types of cone configurations that one could have in general, for arbitrary cone angles alpha, as a function of the continuously variable parameter gamma. All of the defects could be eaten up. As the apex gets more and more pointy, it tends to eat more defects. But if the cone angle is a little bigger, a little closer to pi/2, only some of the defects are eaten, and the K defects remain equally spaced around this concentric ring on the cone flank. And then they could all be there on this concentric ring. And there's an intricate dependence of their positions and their number on P and apex angle. And Farzan found that exactly. And we know he's right. I mean, he knew he was right already, but we know he's right because it agrees with our numerical simulations exactly. So what's shown here is the charge of the flank defects for various values of P. I think Grace chose P equals 2, 3, 4, 5, and 6. There are these jumps where the number of charges on the flank changes as the apex starts to eat things up. These defect charges on the flanks are complementary to the number of defects that have been eaten by the apex. And this is the radius that Farzan predicts as a function, again, of this parameter gamma, where I tune the frustration. So we're pretty pleased that Farzan figured this out. And we think we understand at least what happens at 0 temperature. So I'll conclude with a summary here. As I said, this is work mostly done by Grace Zhang and Farzan Fafa. And I've told you about the analogy with Bohm-Aronoff. Some questions besides the finite temperature stuff that we want to look at in the future is what happens if you put active matter on the cones? What happens to those +1/2 defects? And this +1/2 defect, well, one guess might be if it's consuming energy that it moves along a cone geodesic. And if it's just one of them, it'll of course be perhaps influenced by what happens for this, what happens with this, I need to unmagnify this, but this is all I need for now. What happens when I move on a geodesic for a cone? It's quite interesting. It's like a slingshot orbit of Halley's Comet going around the sun. The sun would be at the apex and it's attracted, but it doesn't get captured, at least if it's a geodesic. And so we think there might be some interesting things to do there. And as someone already mentioned, there's of course the case of hyperbolic cones, which we also find quite intriguing for future directions. So with that, I think I will stop and thank you for your attention. And I would be happy to answer further questions.